Here we are with a view of all the cells and that are in blood. And as you see at the top, we start off with a pluripotent stem cell. And a couple things I want you to notice. One, that when you see this one delineate into myeloid and lymphoid, you see the lymphoid is only for these two cells here, whereas myeloid are for like all the rest. So there's something kind of special about these cells here, and we'll get to that. But if you look down here at the bottom, you see red blood cell. Here's all the white blood cells, all the leukocytes, and here's the platelets. So let's do platelets first because that's pretty quick. Platelets come from a megakaryocyte, and it splinters. So the megakaryocyte is a cell, and it splinters into 2,000 to 3,000 platelet pieces, right? So platelets are pieces of what was a megakaryocyte. And we're going to talk about platelets. First, let's talk about leukocytes, white blood cells. If you see down here, there are, well, they're showing 6. I'm going to count it as 5. So it's all these eosinophil, basophil, neutrophil, monocyte, and then these two I'm kind of putting together as lymphocytes, right? And so I have this on another slide, I believe the next slide. So, by the way, thrombo is going to tell you something about clotting or platelet plugs. So something to do with platelets. So platelets are called thrombocytes. Here's a word, thrombopoietin. So that's going to be a hormone that increases platelet production. Let's take a look at the leukocytes. So there's 5 types of leukocytes, and there are about 5,000 to 10,000 per microliter of blood, right? So you see that I wrote here in green, leukocytosis, that's too many white blood cells. And leukopenia, penia is going to tell you, that word penia is going to tell you not enough, right? And leuko means white. So leukopenia below 5,000. But what I wrote here so these white blood cells, they have different functions. And for example, lymphocytes are going to, they will become also like T cells and B cells. And we'll talk about that when we get to the immune system. But for now, I kind of wrote some things that a high level of these white blood cells might indicate. So you'll see in the book, or even in the previous slide, that I'll go to the previous slide, that they're divided into granular and agranular. I don't know that that's so important anymore, but the difference between, oh, I had it right here. The difference between them is like when you look at them, you see like these little, looks like these little grainy things, right? And so we don't really look for these cells under a microscope anymore. I mean, not in a lab setting. I mean, we could still do it, but you know, it's not, we don't use them to count cells anymore. So what you used to be able to do is look at a white blood cell count, and you can see, you can get an idea of what's going on. For example, if you have pneumonia, you could look at a white blood cell count and you could figure out, you know, is it going to be bacterial or is it going to be viral? So I'm going to be looking for an elevated level of lymphocytes or an elevated level of neutrophils. And that's going to kind of tell me which one it is. And then, you know, because you could treat one type, the bacterial, but not necessarily viral pneumonia. So what you're seeing here, so let's look at this eosinophil. Eosinophil, because it's, they call it that because it's stained by this stain called eosin. You notice that a lot of slides are either like red, purple, or blue, or something on that spectrum, right? Because you have 2 dyes. One's called eosin, one's called, I think, hemotoxin. And so eosin stains red, and then the other one stains blue, and then a combination kind of turns purple, right? And so certain things get stained on the cells, and so the nucleus gets stained. Here you see, like if you were really looking at a cell, this one would be kind of red. It looks like there's 2 nuclei in here, but it's actually 1, and there's like a little isthmus right here. Well, look at this one over here. It looks like there's 1, 2, 3, 3-ish. Right? Neutrophils look like that. It's actually 1 nucleus. It's just kind of, they have lobed. They're lobed. So this one looks like a phone. It does it. To me, it does. If you're older, it looks like a phone. Kids, shut up. All right. So you'll see lymphocytes and monocytes in the future. Monocytes are types of cells called phagocytes or macrophages. Lymphocytes are T cells and B cells. So we're going to see both of those later on. So anyway, in black, I want you to know that, right? So eosinophils are in parasitic infections, and you can read it all. Fungal, here, monocytes high with fungal infections, and then I put TB, tuberculosis, even though that's technically a bacteria. So this is not all inclusive, right? There's other things that high levels indicate, and then there's things that low levels indicate as well. I just kind of wanted to give you an introduction to these white blood cells. We used to take something called a hemocytometer, and we put a drop of blood in it, and then we take one of those squares, like a little square under the microscope, and then we'd count these cells. Now you just put it into a machine, and most clinics have it, and it just pops it out. So those are your white blood cells, leukocytes. Okay, this slide and the next couple are going to talk about coagulation, or really it's our body stopping blood flow. There's 3 ways that our body uses to stop blood flow, and the first is called a vascular spasm. I don't have that as a slide, but what a vascular spasm is you're going to have vasoconstriction right before the damaged part of the blood vessel. So blood vessel gets damaged, blood's leaking out, you're going to constrict the blood vessel before the damage. I don't know why I'm touching my hand and my wrist, but maybe that's helping you understand it, right? So the blood's going this way, there's the leak, constrict the blood vessels, and it can work. Your arteries are really good at constricting, and sometimes people lose limbs. If it's like a clean break, it will your arteries will constrict and retract into the arm, and you'll have minimal blood loss. So anyway, that's called vascular. That's a vascular contraction, vascular spasm. But the other 2 types are the 2 things that I do want to approach. One is a platelet plug, and that is just when your finger gets pricked. And this slide really makes it too complicated. When your finger gets pricked, the platelets aggregate at that site, and they plug up the hole. That's pretty much what a platelet plug is. So it's the collagen fibers. So if you look right here, like I'm gonna go up here. This is the endothelium, right? So here's the endothelial cells. It's a single layer of squamous cells, and then here they are down here. So I don't know. I can't really think of a good example. I mean, I could think of like a building, like a foundation, or like cement in a building. When it gets when you see something getting demolished, right? When the machine hits the cement and the cement tears away, you can see some of the metal rebar underneath it. It's kind of like that. That metal rebar is collagen. Collagen is used to reinforce things and give strength to things. So like in all foundations, you have to lay down metal, and then you pour the cement on top of it, right? So collagen gives strength to things. Same thing in your with your blood vessels, right? Those collagen fibers in there, and so when the epithelial or endothelial tissue gets taken away, damaged, then those collagen fibers stick out, and the platelets pick up on that, and that starts a reaction. And what they do is, if you look at the first slide up here, the platelets are kind of round, and then you look down here and you see how they changed their shape. They're making projections, right? And those projections are allowing them to grab onto other platelets, but they're also releasing chemicals like these little dots in here. That's what that's supposed to be representing. So we have 3 chemicals here, and I've written them here on the side. The first one is ADP. Don't get it confused with ATP, but it's from that whole process, right? So ADP. ADP acts to make other platelets nearby sticky. And so does this chemical called thromboxane A2. I just abbreviated it here, but your book has it. It's called thromboxane A2. Thromboxane A2 activates other platelets. Thromboxane A2, in addition to that, it's a vasoconstrictor. And then you have finally serotonin. Serotonin is another vasoconstrictor. Now, if you know anything about serotonin, you're like, well, no, that's not what it does. Serotonin, like many chemicals in your body, have many jobs, right? ADP has another job. ADP is used to make ATP. But this is like a side hustle that it does. Same thing with serotonin. It's an appetite suppressant, and it stabilizes your mood, and it does a few other things. Here, in this case, it's a vasoconstrictor. So we've got ADP and thromboxane A2. Those 2 chemicals make other platelets nearby sticky. Thromboxane A2 and serotonin are vasoconstrictors. And that's going to ultimately cause the blood to slow down, and it's going to cause all those platelets to stick together. And you have a platelet plug. I don't care so much about platelet adhesion, platelet release reaction, but so there's a platelet, and then look at these threads. So these are fibrin threads. So when a platelet reaction is not enough to stop blood loss, you need to make a clot. But you don't want to make a clot if you don't have to, because clots are kind of dangerous. They're dangerous things. Bleeding to death is also dangerous, right? So, but you don't want to make a clot unless you absolutely have to. So that's going to be really something critical. You're not going to throw a clot because you pricked your finger. But what happens is that when you go to like the next step and you make a clot, you have these fibrin threads, and it makes like a net, and the net catches platelets, red blood cells, white blood cells. They all get stuck in this net, and that whole thing is a clot, or you could call it an embolus. But a bolus is just like a mass of something. Now, I shouldn't have. This is the process, and I was kind of wrong in crossing out all the tissue factors, because they're actually quite important. Knowing some of these tissue factors or blocking some of these tissue factors are important in anticoagulants. But I X'd it out. So let's start here at prothrombinase. This is on the next slide. So at the end of this process is going to start off, we're starting it off with prothrombinase, which is an enzyme. And that enzyme gets produced when there's damage to the tissue that a platelet plug can't handle. Whether it's intrinsic or extrinsic, all that really means is, did the damage come from inside or did the damage come from outside? Right? So most of the time it's going to be extrinsic. But in either case, you end up with prothrombinase. If you look at the next slide, I'm showing you prothrombinase converts prothrombin to thrombin. All right, so we have 2 different meanings. Like, okay, so look here at this word fibrinogen, right? And I was telling you that OGEN is like an inactive form. Well, this is another way to write it. So enzymes are going to end in two ways. ASE, so you see right here, thrombinase, ASE. ASE is like tells you that that's an enzyme. But some enzymes, especially the ones that deal with proteins, they will end with IN, right? So vast majority of enzymes end with ASE, but some end with IN. And so if it ends with IN, you put OGEN after it. If it ends with ASE, you put pro before it. So anyway, the word pro before tells you that it's like a precursor. So prothrombinase it converts this enzyme that you have in you right now, prothrombin, it converts it to an enzyme called thrombin. So you have prothrombin in you right now, but nothing's wrong with you, so you don't want to convert it, right? But once you have some kind of damage that can't be controlled by a platelet plug, then prothrombinase will convert that prothrombin to something called thrombin. Thrombin's going to turn around and convert the fibrinogen in your blood. Remember, that's one of the plasma proteins, fibrinogen. Thrombin's going to convert that to fibrin, right? So you have two conversions in order to start the blood clot. So why do you got to convert things twice? Because it's a very serious thing that your body is doing. You don't want that clot sticking in your brain and stroking you out, or sticking in your lungs somewhere and causing a pulmonary embolism, right? So you want to make sure that there's a reason for it, right? And then plasmin is the one protein that can dissolve fibrin threads. And so when they're trying to give you like clot busters, or someone that's having a stroke, they'll try to give them clot busters if it's not too late. They're giving them a form of plasmin. So that is white blood cells, leukocytes, and thrombocytes. So I'm going to stop this one here.